This meeting is being recorded.
So, in the other sections that were introduced in Chapter 11, 11.1 through 11.3, you may have asked yourself, I wonder what the best approach is, the best process to figure out a synthesis problem. How do I figure out what reagents I need. So for example, here we have these two steps listed here that we can ask. So number one, is there a change in the carbon skeleton? So specifically, is it gaining or losing carbons? So we saw in the last section that we could have a nucleophilic carbon react with an electrophilic carbon to link two chains together in a new carbon-carbon bond. Um, we could also break a carbon-carbon bond with something like ozonolysis. So we could lose carbons effectively. And then the second question here that we'll look at is there a change in the identity or location of the functional group? So are we completely changing it from, an alkyl halide to an alcohol? Are we changing the identity? Or are we just relocating that alcohol group or that halogen or the pi bond? So not only can we change a functional group, we can also relocate. So let's take a look at how this would play out in this example here. So we are asked to propose an efficient synthesis. So again, efficient, I had mentioned in a previous video, means the least steps, the easiest, the fastest way to get there. So let's see here. So this is my starting material over here, and we're noted to have 1, 2, 3, 4, 5 carbons in this carbon skeleton, in this longest carbon chain. Our product over here now has 7 carbons. So we've had to add 2 carbons to our 5 carbon starting material. So we know that there has been a change in the carbon skeleton. Let's see what else. Was there a change in the identity or location of the functional group? Well, we had an alkyne over here with our CC triple bond, and this has been changed into specifically a trans alkene. So we need to think about not only how do we add on those additional carbons, but then how can we convert from a triple bond to a double bond, specifically in the trans orientation. So we have to move around our functional groups, and then we also need to add additional carbon. So how can we approach this? How can we attack this? So we see here with our starting material, we could use sodium amide in our first step here and create our nucleophilic site here on this carbon. And then if we add, in this case, we have ethyl iodide or iodoethane here used in step 2. This could be chloride, bromide as well, ethyl chloride, bromochloride, and I'm sorry, bromo ethane as well. So either of these could be used, and that would provide us with those 2 carbon atoms to increase our carbon skeleton. So these 2 carbons over here have been added through these 2 steps. So we have accomplished the 7 carbon chain that we need to have for our product, and then we can take this new material, this intermediate product that we have, and subject it to dissolving metal reduction conditions. So we have our sodium metal and then our liquid ammonia here, and that will produce a trans alkene. So we can see that all in all, we can say that it's 2 steps. The first, adding those extra carbons, but it's really 3 reactions overall. So first step, add the carbons. Second step, convert alkyne to a transalkene, but we had to use 3 steps to get there. So all in all, you may see a problem that looks like this, where you have your substrate over here that I just circled, and then we see just 1, 2, 3 steps listed one after the other. So we know, so we should know with sodium amide what results, right? We have that that nucleophilic site created, and then we have here where we add using this electrophilic carbon here in the ethyl iodide. So, and then our last step, of course, is that sodium metal dissolve to convert to our trans alkene. So many problems will involve 2, 3, 5 steps at times to convert from our starting material to product. So we'll take a look at some practice problems from this section, and then we will continue with 11.5 in the next video.